Hey everyone, so today we're going to dive into a really cool fundamental challenge in chemistry, which is how do you possibly count something that you can't even see? We're talking about atoms, about molecules, and the totally clever way scientists figured out how to, well, weigh the invisible. No, I mean, really think about that for a second. Chemists have to know exactly how many atoms are in a reaction, but it's not like you can just, line them up and tick them off a list. So how on earth do they manage it? To give you some perspective on the numbers we're dealing with, just imagine trying to count this many marbles. We're talking about a number so ridiculously vast. That's over 600 sextillion. You couldn't count them in 1,000 lifetimes. And atoms? They're infinitely smaller. This was the huge problem that chemists were up against. And that brings us to our first big idea here, the impossible count. Trying to count atoms directly is, for pretty much all practical purposes, impossible. So science needed a smart workaround. And you know what? That workaround is a concept you already use all the time. When you buy eggs, you don't ask for 12 of them, right? You ask for a dozen. Dozen is just a convenient word for the number 12. Well, chemists needed their own dozen, just for a mind-bogglingly huge number of particles. So this brings us to the real hero of this story, the chemist's dozen. It's a special counting unit designed from the ground up just for the atomic scale. And that unit is called the mole. And no, not the furry little animal that digs up your backyard. In chemistry, a mole is just a word for an amount of stuff. To be specific, it's the amount of a substance that has one very special, very, very massive number of particles in it. And here it is. This is the magic number, 6.022 times 10 to the power of 23. This is known as Avogadro's number, and it's the exact number of particles, whether we're talking atoms or molecules, in one single mole of anything. And this quote really gets to the heart of why the mole is just so brilliant. It's the bridge between two completely different worlds. It lets a scientist count individual atoms just by measuring out an amount of stuff in grams that they can actually see and handle on a lab scale. So if we can't count the atoms one by one, but we know exactly how many are in a mole, how do we get precisely 1 mole of something? Well, we don't count it. We weigh it. This is where the whole idea of molar mass comes into play. It's actually super simple. It's just the mass in grams of 1 mole of a substance. This is the practical key that makes all of this work. If you know the molar mass, you can weigh out that amount and know exactly how many particles you're holding. And calculating it is surprisingly easy. All you need is a periodic table. Step 1, just list out the elements in your compound. Step 2, look up the atomic mass for each of them. And step 3, add them all up. That's it. Let's try it with a classic example, water, or H2O. Okay, so looking at the formula, we've got 2 hydrogen atoms, and each has an atomic mass of about 1. And we have 1 oxygen atom with a mass of 16. You add it all together, and you get 18. That means the molar mass of water is 18 grams per mole. So if you weigh out 18 grams of water, you know for a fact you have exactly 1 mole of H2O molecules. Okay, so once we've got the molar mass, we basically have a complete toolkit for jumping between all these different ways of measuring stuff. You can almost think of it like a roadmap for your chemical calculations. And this whole toolkit revolves around the mole. You can use the molar mass to get from the mass you can weigh in a lab to the number of moles. And from there, you can use Avogadro's number to figure out the exact number of particles. These conversions are basically the engine that drives quantitative chemistry. Okay, so this is all really neat for chemists, but why should you care? Well, it turns out this whole mole concept is actually critical in a ton of different parts of our daily lives. Take medicine, for instance. A drug's effectiveness is all about how many molecules of it get to the right place in your body. Dosages are calculated incredibly carefully using molar mass to make sure every single pill has the perfect number of particles to be effective, but also to be safe. It even shows up in your kitchen. Baking is really just delicious chemistry, isn't it? A baker who gets the mole concept can predict exactly how much carbon dioxide gas their yeast is going to make from a certain amount of sugar, and that leads to the perfect rise in a loaf of bread. And on an even bigger scale, environmental scientists use the mole to measure pollutants. When you hear them talking about CO2 concentrations in the atmosphere, they're using these exact same principles to count carbon dioxide molecules, so they can understand their impact on our climate. See, the mole gives us a kind of superpower, the ability to count the invisible and link it to the world we can actually see and touch. It turns chemistry from guesswork into a really precise science. So, as you look around you now, what invisible things can you imagine being able to measure and understand? And that's our look at Avogadro's number and the incredible power of the mole. A huge thank you to Flying Wings Online School for providing the source material for this explainer. Thanks so much for watching.